All right, today we are going to talk about feedback current amplifiers. Oh, shit. All right, let's see. Sorry, having some technical difficulties. All right. Whatever. All right, sorry about that. So as I mentioned a moment ago, we are going to be talking about feedback current amplifiers today. So for a feedback current amplifier, we are measuring or sensing current at the output, and we are going to have to connect our feedback mechanism in some way to add currents at the input. So what is our feedback topology going to be? So at the output, since we are measuring a current, how do we measure a current? Series or parallel? Series, right? And then at the input, because we're adding another current signal, we need to do that guy in parallel, right? Okay, so with that in mind, we're going to have a parallel series feedback connection, which is going to look something like this. So here is our signal current, I sub S. Here's our open loop resistance R sub I, over which we will have a voltage drop V sub I and a current flowing through it. I sub I over here on this side, the output port of our open loop amplifier contains a dependent current source, A1 times I sub I in parallel with the open loop output resistance R naught. Here are the terminals of the output of the system. We're going to short circuit it because we're connecting things in series. Here's our output current, I out. And so we can see that this is the current I out flowing along its return path. So we have the sense mechanism taken care of. On the input side, we are going to have a dependent current source providing our feedback signal, a I out like so, and it's connected in parallel, where this is our feedback current I sub F. And if we were to look in through this terminal, here we would see the input resistance with feedback. Similarly, if we looked in through the output terminals, we would see the output resistance with feedback. And just to be clear, everything I'm boxing in here in orange is my approximation of my open loop amplifier. And everything that I'm going to box here in purple is my feedback network. All right, I think I got everything covered there. So as discussed a couple of minutes ago, the feedback network is connected to the input of our system in parallel and the output of our amplifier system in series. The ideal representation of this system, or the equivalent representation of this ideal system, would be a better way to put it. Look something like this. So here's S, here's S prime. Here's RIF. We know that IS is flowing into it. AF, IS, I out, and finally, here is our OF. So in order to get to our equivalent circuit, we obviously need to figure out what our gain with feedback is, our input resistance with feedback, and our output resistance with feedback. Anybody care to venture a guess what our input resistance, or excuse me, what our gain with feedback is going to be, just based entirely on our previous discussions? We need to derive it, we can, but it should be fairly obvious what it's going to be at this point. Anybody but Brian have a suggestion? What's it going to be? What is our closed loop gain going to be? What has it been for every one of these damn things? A1 over 1 plus KA1 every single time. We can prove it very trivially here, right? I out will be exactly equal to A1 times I sub I, where I sub I is IS minus IF, where IF is KI out. So we have I out is equal to A1 times some crap. The KI out is going to move over, and we're going to wind up with A1 divided by 1 plus K A1. If we don't get this, we have done something terribly wrong, because the whole point of this is to make it look like a simple negative feedback circuit, which is what we've been doing this entire time. Our input resistance with feedback by inspection, what is it going to be? RIF, yes, but how does that relate to the open loop input resistance RI? So we're connecting this guy in parallel. The feedback network is in parallel, right? So does that mean it's going to boost the resistance or make it go down? It's going to make it go down. So by inspection completely, we can see that RIF is just RI over 1 plus K A1. What about our output resistance with feedback? We have a series connection at our output, right? Does the series connection boost the resistance or decrease the resistance? Boosts it, right? We're putting some resistance in series. Okay, so that means we're going to have RO times 1 plus KA1. So these are our ideal values, okay? At this point, I believe we've beaten how we get these things to death over and over again. So we can tell completely by looking at the sense and return mechanisms as to how all of these things are supposed to behave. All right, so with the ideal case out of the way, let's look at our practical case. Our practical case is where we have some non-zero signal resistance, which I have included. Here's terminal S prime. If we look in here, we see RIF. If we look in immediately after our signal resistance, we see RN. Here is our open loop amplifier. On our load side, we're going to have some resistance R sub L. So in this case, we're treating it as if it were not infinitely large. This is where I can look in to find R not F. If I look in instead at the terminals where RL was placed, that's how I determine R out. Here's my feedback network. So this guy's connected like this, where just to be clear here, this is I out. And port 1 is connected in parallel. Like so, here's 2. And just to specify, here's IF. Here's I out, and I have all my resistances taken care of. Okay, so this is what our system is going to look like in a practical case when the feedback network is considered to be loading the input and output port of our amplifier. Obviously, we're going to have to figure out how to calculate R11, R22 feedback factor and the open loop gain circuit. What do you think is going to happen with our feedback network? Or, so determining, let's say we're determining R11, okay? We have our feedback network like so. Here's port 1. Here's port 2. Typically speaking, when we're measuring R11, we're looking into port 1. So that's kind of a given. So the question is, you guys think that port 2 should be open or closed here? Right. Actually, no, sorry, I take that back. When we're looking at it with a series connection, we have to have it open circuited. When we're looking at it with a parallel connection, we have it short circuited, right? That's the what we've been doing. That is what we've established to this point. So because we have a series connection to our output, we're looking at it with an open circuit. So we're literally just looking into port 1 and seeing what's going on. Okay. To measure or determine R22, here's 1, here's port 2. We're going to look in to port 2 with port 1 short circuited. All right. Our feedback factor, K, is determined as follows. So we have our feedback network. Bless you. Here's port 1, here's port 2. We apply a test current, which I'll call I out. We're going to measure the feedback current, which I'll call IF, and we have to impose the restriction here that the voltage drop across port 1 is 0 volts. So because we have a current amplifier, this actually looks a little bit different than what we've seen before. I just want to be clear about that. Our feedback factor, K, is then going to be defined as I out over, IF over I out. My apologies. Where V1 is equal to 0 volts. From this, we can get our open loop circuit. On the output side, because we have a series connection, we should see RL and R22 connected in series. And if we look in, like if we broke that open and looked in, this is how we would measure our output resistance, our open loop output resistance R out. On the source side of things, because we have a parallel connection, we should see RS and R11 connected in parallel. Here is I sub I. Looking in through here is how we measure RI, and our open loop gain will be by definition. Sorry, let me specify where things are flowing here. I out over I sub I. And then from here, we obviously know how to measure. Once we know we can measure R naught and RI, we can measure ROF and RIF. And so now we really just need to relate things back to R out and R in, as it were. So we can see that R in is just RIF with RS in parallel, right? So we got to take that RS out. So this gives us R in is 1 over RIF minus 1 over our signal resistance to the -1 power. Similarly, R out, we have ROF in series with RL, so we got to take the RL away. So we have ROF minus RL, okay, if we wanted to determine the effects of just the system. All right, so I have a couple of example problems to work, and then we'll be wrapped up on this topic, all right? So let's look at this first example. Here is VDD. Here is some resistance R sub D. Here's our transistor M1. Here is transistor M2. Here is our input current IN. Here is our output current of interest I out. And if we look in through here, so effectively if we look in through the open circuit terminals, if we had turned our IN off, this will be our resistance RIF, excuse me, because we don't have a signal resistance to deal with. And similarly, this is the place that we're going to be looking at or breaking open to determine our output resistance ROF. Let's work this problem under the assumption that lambda 1 and lambda 2 are equal to 0. Okay. So what does our feedback network look like in this system? Here's port 1. Here's port 2. Yeah, so R1 is connecting port 1 to port 2 because it's the one that's connected from the output to the input or the gate of transistor M1. So that is going to look like this. Here's resistor R1. Where's R2 going to be located? So I would say that it goes right here, right? Because it's connected from the output port to our ground. So our loading resistance R1 what? We are looking into port 1 with port 2 open. What do we see? Series connection. So R1 in series with R2. To me, this is the configuration where the feedback network makes the absolute most sense, right? And so let me explain what I mean by that. We have our input current IN flowing into this node. We know that none of it can branch off and flow up, right? So that means all that current's going to flow through R1 and sees a path R2 to ground. So it makes sense that the loading effect looks like just R1 and R2 in series with our input current source. What about R22? We're looking into port 2 with port 1 short circuited. They're in parallel. R1 in parallel with R2. Feedback factor is going to be a little bit more difficult to do, not wildly so by any stretch of the imagination. So if we had a test current source applied to port 2 with the direction up, we short circuit port 1 and we're trying to find the current that's flowing up into port 1. What's it going to be? So we can use current division, right? 1 over R1 divided by 1 over R1 plus 1 over R2, which is the exact same thing as R2 over R1 plus R2. Let's think about the directions here. Okay, so let's start by saying we have R2 over R1 plus R2. Anybody got a problem with that? That is the direct result of applying current division and finding how much is going to split off and flow through that resistor R1. But we know that I out has this direction and IF has this direction. So we need to include a negative sign as well. Okay. Now this is interesting because this is our first negative feedback factor that we've experienced. Okay. So if we think back a couple of weeks ago, talking about the concept of the loop gain, where the loop gain was just A1 times K. Its polarity or its sign determines whether or not we have positive feedback or negative feedback, right? Because if we look at the denominator of our closed loop gain, it's 1 plus K A1, all right? So if K is inherently negative, if A1 isn't also negative, we actually have positive feedback, which is a problem, okay? So we should expect to see that our open loop gain of these systems inherently needs to be negative in order for our system to have negative feedback. All right, so with that in mind, let's discuss what our open loop circuit looks like and then calculate our different parameters. All right, I called that IN, should be consistent. And over here, one and two. Here's I out. So we're going to see our loading resistance R11 between the gate and drain, so the input port and drain. And we are going to see the resistance R22 between the output port and ground. Sorry, I may have said drain, I meant ground. So between the gate and ground and between the output terminal of our amplifier and ground here. Okay, so I might be breaking this down too simplistically, but I just want to be clear about what's going on here. I'm going to call this node node X because we are going to have some transfer function that is converting that input current into a voltage that is then applied to the gate of transistor M1, right? Then let's call this guy node Y so that overall our open loop gain should be Vx over In multiplied by Vy over Vx multiplied by I out over Vy. So that our overall transfer function represents I out over In, which is exactly what it should be for a current amplifier. So, which one of you soon-to-be senior electrical engineering students can tell me what my transfer function Vx over In is? R11, that's it. R11, that is it. All right, so that's what that resistor does, is literally convert that input current signal into a voltage, which is applied at our gate. What is our transfer function for our second stage, which is effectively just the transistor M1, right? So it's Vy over Vx. If we put a dashed line here, and we're only looking at everything to the left, where we're treating just node X as a voltage source, because that's what it's behaving as, what do we have? Common source amplifier. No degeneration or anything fancy to worry about. So what's its gain? Negative GM-RD, right? Common source is negative GM-RD. Common gate is positive GM-RD. It's important. Yes, very important, specifically because it's negative here. That is correct. So negative GM1 because it's the transconductance of transistor M1 multiplied by RD. For I out, so I out over VY is a little bit more difficult to figure out here, not wildly so. We know that I out small signal is going to be GM2 multiplied by VGS2 because that's what a transistor is meant to do, right? So the voltage at the gate of this guy is VY. The voltage at the source is I out times R22. And so from this, we can see easily that I out over VY is GM2 over 1 plus GM2 R22. Two little easy peasy algebraic steps that I've skipped there. Hopefully at this point you guys are catching what I'm throwing. So if I put all three of these stages together, multiplying them, my open loop gain A1 is negative GM1 GM2 RD times R11 divided by 1 plus GM2 R22. What is my open loop input resistance? So to be clear, we're looking in right here to find RI, and we're looking in right here to find R0. What is RI? Just R11. Okay, right? So I like where your head was at, Nathan, but we have R11 in parallel with something that's infinitely large. So it's just going to be R11. Now, if we were doing this with BJTs, we would need to include what we see at the base there. But we're doing MOSFETs because the math is much easier. So this is just going to be R11. That is literally the reason. Is just I don't want to have to deal with R pi 7,000 times. What is our output resistance? Our open loop output resistance are not going to be. We did a couple of these on Friday, right? So just to be clear here, we would break this guy open and then look in, because if we don't, we see everything in parallel with a short circuit, right? So we break this guy open, and what we see going up is in series with what we see looking down. So what do we see looking up? 1 over GM2, because we're looking in the source terminal. What do we see down? R22, nothing wild or crazy there. And we have now analyzed this guy enough to be able to determine the closed loop gain, the closed loop feedback, the closed loop input resistance and closed loop output resistance and all that kind of jazz. So we are effectively done analyzing the circuit. Nathan, what's up?
I'll get the error pointing that way. Whenever I see it go that way.
Right, so the key here is that we are looking at a current system, okay? So let's look back up here, all right? I try to find my open loop resistance with feedback by breaking this set of terminals and seeing what is connected to this open loop or this open set. So I'm going to see whatever part of my feedback is and then RL effectively in series with it when I go around the path. If I look at this guy right here, which is representative of my open loop circuit, again, I'm breaking this point here because if I don't, I'm measuring RL in series with R22 in parallel with a short circuit, which is always just going to look like the short circuit, right? So I got to break this guy open and look in, which shows me that RL would be in series with R22 or R22. So I'm doing the exact same thing in my transistor amplifier. So that's a good question. All right, so any further questions on this first example problem? Nothing too wild or crazy, I don't think. Nobody's saying anything. Let's move on to a second example problem. All right. Here is RD. Here's some DC bias voltage, which I'm going to call V bias. Resistor M2, so over here will be M1. Dealing with another laser diode control system. IN, I've talked about where I out is. So here's where our IF would be. This point looking in would be where our OF would be. Okay. So I want to point something out here. This transistor M2 is a PMOS transistor. Can anybody tell me why I absolutely have to have a PMOS transistor there? No. I have a common gate amplifier there as my first stage, which inherently has a positive gain, right? So the PMOS transistor is responsible for giving me a negative coefficient so that my open loop gain will wind up being negative when we look at this guy, okay? I'll talk about it a little bit more as we do the analysis. Our feedback network is going to be literally identical to our last one, right? There's no change whatsoever. So we can easily see that at port 1, here's port 2, this is R1, this is R2. We know that R11 is R1 plus R2. We know that R22 is R1 in parallel with R2, and we know that K is negative R2 over R1 plus R2, because it's literally identical to the last problem, so there's no need to suffer through figuring it out again, okay? So for my open loop circuit, here's RD. Bias voltage. So there's all that kind of good stuff. My diode is going to have some dynamic resistance, lowercase rd, and then there's where R22 is. Sorry, I made that look like it has two arrows, which would be wildly confusing to analyze and would mess things up. All right, so this is my open loop system. I can again break it into three stages. My first stage converts my input current to a voltage. My second stage takes my input voltage Vx and converts it to some output voltage Vy, where Vy is the input voltage of my final stage. So here's M1, here's M2. Just to be clear, here's I out, here's R naught, here's Ri. So overall, we're going to have A1 is equal to Vx over In times Vy over Vx times I out over Vy, just like the last system. Vx over in this case is going to be the exact same value as it was previously, just the resistor R11, because its whole job is to convert that current to a voltage. Vy over Vx. What's that going to be? Positive GM1 times RD, okay? Because we have a common gate. And now we can approach the output current relationship much like we did the last one. We have a PMOS transistor, right? So I have my current flowing. I'm just going to call this guy ID, representative of my drain current. It is flowing from my source to my drain, okay? And so this should be GM2 times VSG2, because I'm dealing with a PMOS, right? So VSG. So what's the voltage at what's the AC voltage at the source? 0, because the source is at the highest potential, so it's at VDD, which is a DC, so we treat it as an AC ground. So we're going to have 0 minus the voltage present at the gate, which is VY, giving me a transfer function of I out over VY is equal to negative GM2. So this is where, if I don't have a PMOS transistor for M2, I don't have negative feedback. Okay. So it's absolutely critical. Everybody okay with the way that I derived this transfer function? Anything seem odd? It shouldn't, but I just want to make sure everybody's on board. Okay. So if I multiply through my three transfer functions together, I have A1 is equal to negative GM1 GM2 RD times R11. What is my open loop input resistance? R11 again. Okay. So that is a fantastic point. Yeah. So now we do see a path that isn't an open circuit here. Okay. So we have R11 as a path from this way to ground, and then we have something else this way. I believe it should just be 1 over GM1. Yes, because this. We're just looking in through the source. That is grounded. Yeah, so just 1 over GM1. Thank you. R11 in parallel with 1 over GM1. Sorry. And what about our open loop output resistance R0? So what do we see when we look into the drain of a transistor? And we're assuming here that we don't have channel length modulation present to be infinitely large, right? So let me explain exactly what I'm talking about here. If we were looking at just transistor M2, we're trying to find the output resistance. So we're setting our voltage present at our gate, which is the input resistance, equal to 0. Here we have VSG2. This is our source. So this is S2. And then we would have current is flowing from the source to the drain, so this should be up. My apologies, GM2, VGS2. And we're looking in. So what's VSG2? It's 0. So we see an open circuit. So we actually have an infinitely large output impedance here. Okay. What if channel length modulation were included? R02 plus RD plus R22 if lambda 2 does not equal 0. While we're at it, if we're including the effects of channel length modulation on transistor M2, we might as well figure out what's going on with channel length modulation effects included on transistor M1. I guess we could get around this by just having our NMOS transistor have a very large channel and our PMOS not. But, you know, let's just, for completeness' sake, see what's what when we have channel length modulation included. So for transistor M1, okay, we're looking in through the source, and we know that whatever we see is going to be in parallel with this resistance R11. So I'm not going to bother drawing that. We're going to just make a mental note that whatever we see is going to be in parallel with that guy. All right. So my gate terminal is grounded for sure. Because we're dealing with a NMOS, we'll have VGS1. This is the source where we're looking in. This is GM1, VGS1. Our channel length modulation resistance, R01, should be here. It is connected between the drain and the source, right? And then we also have that resistance RD between the drain and ground. And just for completeness' sake, also connected to the drain is whatever we would see looking this way, which is going to be an infinitely large impedance. Okay. So just wanted to be clear that we technically should take that into account as well. All right, so I'm going to call this guy RI. prime because it does not include the R11 that we know should be there. So what's going on here? How can we figure out what this input resistance is? What's the most easy path to do it? Test source, right? Okay. So if I apply a test source, let's call it Vx, the current flowing out is Ix, and the resistance Ri prime is just going to be the ratio of Vx to Ix. This node right here is our source of transistor 1. This guy right here is going to be ground, which I'll call the gate of transistor 1, so that we can see pretty easily, just to be clear here, that VGS1 is a negative Vx. All right. Then we have, I'm going to have to draw this like this. Our resistance R01, and it is in parallel GM1, VGS1, and let's see, the arrow is pointed to the source, so the positive polarity terminal should be the one connected to the source. The negative polarity terminal would be the one connected to the drain. So this is our drain node here. Here's our resistance RD. And this is what we got. Anybody have any problem with this drawing? Let's start there. Oh, it's a current source. Yeah, sorry. I was getting ahead of myself. Yeah, I'm going to do a source. Yes, exactly right. So I feel like I could probably analyze this circuit, but I know for sure that if I do a source transformation here, I have an easy peasy single loop circuit that I can analyze all day long. So I like to do a source transformation whenever I have this guy in parallel, because it just makes me have to think less opportunities for mistakes. So you guys caught me on my stuff. All right, so with that in mind, going ahead and doing the source transformation, here's Vx, here's Ix, plus minus, so I'm going to call this guy GM1 times negative Vx. I'm already just substituting in the fact that VGS1 is equal to negative Vx. And then I have to multiply this guy by R01. And that is going to put R01 in series with RD. So this is what I have. Everybody okay with that? So if I do Kirchhoff's voltage law, I have negative Vx minus GM1, sorry, plus GM1 times negative Vx times R01 plus R01 plus RD times Ix is equal to 0, which looks like Vx times 1 plus GM1 R01 is equal to R01 plus RD Ix. Therefore, Ri prime, which by definition will be Vx over Ix, is going to be R01 plus RD divided by 1 plus GM1 R01. So coming up here, that gives me R01 plus RD divided by 1 plus GM1 R01, all in parallel with R11 if lambda 1 is not equal to 0. Working it with channel length modulation included, just to make things more difficult and fill out some time, because I don't have anything else prepared. So, all right, so all we have left then is Wednesday will be transimpedance amplifiers. I feel like we'll probably wrap those up within 45 minutes, and then we can use the rest of the class for review. So before we get out of here for today, we are leaving 20 minutes early. Anybody have any questions or anything about any of this business?
So, go back to so EX over I, should that be R11 parallel to 1 over GM? Does it see a path of 1 over GM resistance route up the transistor?
I believe, no, I understand what you're saying, and I think you are correct. I think I just jumped and threw R11 there because it was easy. Yeah. So the question here is the resistance. We're effectively looking for the input resistance that we see here, because that is what's going to convert that input signal into our input parent signal into an input voltage signal at this node. So if we see 1 over GM looking up in parallel with R11, that current will get multiplied by that equivalent resistance, giving us the voltage present at node X. So you are correct. It should be R11 in parallel with 1 over GM. And that would then be included there. You're right. Thank you for catching my mistake on the exact same thing twice. You're absolutely right. If anything, if we're assuming, typically speaking, the transconductance is on the order of, tens of ohms or 1 over tens of ohms, and our feedback resistors are usually on the order of kilo ohms, we can approximate this as 1 over GM1. And so our overall voltage gain for our system would actually be closer to negative GM2 times RD for most cases, unless we chose specifically small values of feedback resistors. What's up? Okay, so that's a fantastic question. So let's look again what we have here, okay? So I'm breaking things open after my load resistance, but before I see R22 or R22. The load resistance in this case is the dynamic resistance of the diode. So that's why it needs to go after the diode. A short circuit. Okay, let me scroll up again to our original thing here. Maybe this will potentially clarify things as well, okay? So we are looking for a place in our loop system after the load resistance, but before we're connected to the feedback network, which is exactly the place that I've drawn my arrow to measure R0 and R0F. So these are the constraints of where we're looking into our system. Okay. So if I consider, if I were looking in here, that would be effectively me saying that I'm lumping in the resistance of my diode as part of my feedback network. But I know that that can't be true because it's not connected from the output terminal to the input terminal in any way, shape, or form. right? If I erase this guy right here and replace it with some load resistance RL, it's representative of the resistance of the diode, right? This represents the point between where my load is connected and where my feedback network starts. Does that make sense? Okay. Pardon? I don't understand your statement there by what you mean one node wide.
So like there's one node to the left of R1 and then one node to the right.
Yeah, so effectively between here and ground is port 1, and between here and ground is port 2 of our feedback network. And that's how we've been doing it for all of the examples, regardless of our configuration. So there's something between this node with ground as a reference and this node with ground as a reference, and that's why it shows up here, connecting 1 to 2, where maybe it would be more obvious if I just said that. So I have this node, which has an associated voltage with respect to ground, which is what we've been dealing with and all that kind of stuff. And then this node has an associated configuration with respect to ground. So that's why R2 is where it is. And then again, R1 is between the upper terminal of port 2 and the upper terminal of port 1. All right. Any other questions? Excuse me. All righty. I'll see you guys on Wednesday.